Welcome back to another explainer. All right, let's jump right in. Before we even look at the details today, I want you to take a quick second and just imagine something for me. Think about the massive, mind-bending logistical challenge of sending a huge, high-definition video file to a friend sitting halfway across the world. You tap send and boom, it arrives in seconds. It literally happens in the blink of an eye. But the actual mechanics behind that one simple action, they are absolutely wild. So how exactly does a massive video file squeeze through those invisible airwaves right to your phone? It's a really fantastic question, because here's the thing. A massive file simply cannot travel all at once. There is no giant magical digital pipe out there pushing that huge file through in one big solid chunk. And honestly, that reality sets up the ultimate mystery for us today. How does our data actually move across networks and between our devices? Okay, let's dive into this. Here is our roadmap for today. Number 1, breaking down the data. 2, inside a data packet. 3, the packet switching journey. 4, methods of data transmission. And 5, understanding the USB.
Starting off with Section 1, breaking down the data.
So right off the bat, data simply cannot travel in one piece. It has to be dismantled into manageable blocks, which we call packets. You can think of digital information kind of like a massive cargo shipment. If you're shipping an entire factory's worth of goods, you don't build one giant, impossible megatruck to carry the whole thing, right? No, you break the massive shipment down into standard, manageable shipping containers so they can actually travel efficiently over the roads we already have. In our digital world, these standard containers are packets. And to put that into perspective, a single standard packet carries only about 1,500 bytes of data. That means a super short video requires literally millions of these digital shipping containers to be generated instantly.
Let's move to Section 2 and see how this builds inside a data packet.
Every single packet relies on 3 fundamental components: the packet header, the payload, and the trailer. Using the classic postal system metaphor as a quick refresher here, the payload is your letter. It's the valuable item you're actually trying to send, the core data itself. The packet header serves as the carefully addressed envelope, complete with all the routing instructions right on the outside. And the trailer? Well, that acts like the wax seal or an official signature at the end, securely closing up the package. Now, what's really fascinating here is the packet header, because it essentially acts as both the GPS and the return label for this tiny chunk of data. First, it contains the destination address, so the packet knows exactly where it's trying to go. Next, it contains the originator's address, so the receiving device knows exactly who sent it. And lastly, it contains a packet number. I want you to keep that packet number in the back of your mind, because it is incredibly important for making sense of what happens next. Which brings us to Section 3, the packet switching journey. Okay, let's map out this incredible, honestly kind of chaotic, journey of packet switching. Step 1. As we know, the data is broken down into packets. Step 2. They're blasted out into the network, where devices called routers take control of the routes. Picture a router as a highly caffeinated traffic cop, rapidly analyzing the network and sending packets down totally different roads just to avoid congestion. And because every single packet can take a completely unique route, we arrive at Step 3. Packets may actually arrive out of order. Seriously, packet number 5 might hit 0 traffic and beat packet number 1 to the destination. Finally, Step 4. Once the very last packet has arrived, all of those packets are carefully reordered. And how do they do it? By using those crucial packet numbers we saw embedded in the header just a minute ago. They are magically reassembled right at the finish line into that seamless video you watch on your screen. Next up, Section 4, methods of data transmission. So now we need to contrast the extreme rules of the road. On one side, we have simplex transmission, which is strictly one way. Think of this exactly like a physical one-way street in a city. Traffic can only ever flow in a single direction, never back. On the total opposite side, we have full-duplex, which allows for simultaneous two-way transmission. Full-duplex is just like a standard two-way phone call. Both people can talk and listen at the exact same time without interrupting the flow of the conversation. But what if your needs sit right in the middle? Well, then you use half-duplex. Data transmits in both directions, sure, but only one direction at a time. It works exactly like a walkie-talkie. Pressing the button to speak temporarily blocks incoming signals, right? Both devices can send and receive, but they simply cannot do it simultaneously over the same channel. And this perfectly illustrates the inherent trade-offs in network design, especially when we pit serial against parallel transmission methods. Serial transmission sends data sequentially down a single wire, while parallel sends multiple data bits simultaneously across multiple wires. The huge advantage of the serial method is its incredible stability over long distances. The catch? It's generally slower. Parallel, on the other hand, gives you that awesome multi-lane speed as an advantage, but comes with a distinct disadvantage. There is a much higher risk of data errors and interference. So choosing what suits you best really comes down to whether you need the single-lane stability of serial or the multi-lane speed of parallel. Finally, Section 5, Understanding the USB. The Universal Serial Bus, which, let's be real, we all just call the USB, is the ultimate everyday data gateway. This is the critical physical bridge we use to actually transmit all of this data. All those millions of packets moving in simplex or duplex, this is how they get into and out of our personal devices. It's so ubiquitous today that we completely forget there are billions of these physical bridges actively shifting data right at this very moment. The USB is a universally standardized interface. That means it's been adopted globally to transmit data across a totally massive ecosystem of hardware. And this brings huge benefits. It's incredibly versatile, it's automatically recognized by most devices, and it can safely provide power while simultaneously transmitting data. Talk about multitasking. However, we do have to recognize it comes with physical drawbacks, like limits on maximum cable lengths before the data starts to degrade, or, the historical annoyance of those older connector shapes that only plug in one specific way. Still, it absolutely remains a marvel of everyday data transmission. Wow, we have unpacked a massive amount of technical logistics today, basically taking the invisible and making it visible. So I want to leave you with this final provocative thought. Next time you plug a simple cable into your computer, will you picture the millions of packets racing through those invisible highways? It really is amazing to realize the incredibly complex digital logistics we trigger with just a simple click or a plug. Thank you so much for joining me for this explainer. Keep learning, keep visualizing the world around you, and I will see you next time.